So, um, we're going to look at the next application of integration, which still is volume, but instead of stacking up our areas, right, stacking up these little thin sheets of paper, if you will, to get the volume, we're going to take a region and then we're going to revolve that around a center of axes and rotate that. And so, so I'm looking over here at this almost a triangular shape, and if I take that region and if I somehow were able to rotate it and watch that image go around, that's what we're going to try to create. And so I have a couple, it's like showing how would you construct that, right? And so just kind of watching, just kind of see, okay, here's what we're making. We are making just like a bunch of discs or a bunch of washers and stacking them up. So everything that we are I guess adding up in terms of area is going to be circular. Okay, everything's going to have some kind of like pi r squared or part of pi r squared. But notice you're originally starting with just a region, and you're going to still be measuring top minus bottom, but you're going to be measuring that compared to the axes of rotation, and that's going to be key. And so we're going to start looking at some of these examples, and it'll probably take a couple days till we really get good at doing this. So let's go ahead and we'll start looking at some notes. And so this is just in your workbook. And like this very first example just comes from geometry. It says find the area of the shaded region, show your work. And so it's two concentric circles. They have the same center, one radius 10, one radius 6. And I want the shaded area. And my hope is that you're able to pause the video and then find it, and then let's see. But what I want to think about this in terms of area is finding the area of the large circle, right? So if I find the area of this large circle, the circle that does have radius 10, right? So the area of the large circle, maybe I'll use like a pi big R squared. And then I'd like to then take away the area of the small circle. So if I can take that smaller circle away, all that I'll have left is this almost like this donut shape, right? You can tell it's breakfast time. This donut shape ring, that would be, I guess, it'll be left over from doing big circle minus little circle. And so my hope is that you see that okay, so I could take away the little circle. And so the big circle had a radius of 10. So I could say, okay, that's 100 pi minus, and the smaller circle had a radius of 6, 36 pi. Okay, so 100 minus 36, so I get 64 pi as my area. And I hope that you see that it's not doing, this radius was 10 and this radius is 6, 10 minus 6, so this distance is 4, which that's true, but I hope you realize that's not going to be pi times 4 squared, which is 16 pi. Because that sometimes happens. That's sometimes what some students think maybe to initially do. So don't do that. But the other thing I want us to notice, and this is going to help us when we start setting up our volume down below, is that there is a pi in each of those factors. That I could have taken out a pi, factor out pi first. That I could have done. So I could have said, okay, let's take out pi. And then I have big R squared minus little r squared, which was pi times 100 minus 36 to get 64 pi. Okay, that piece actually is really important because I'm gonna really go back and talk about, okay, there's the big R and there's the little r, big R and the little r, and they're just two circles, one embedded in the other. Okay, so hardest part about this section is the setup. Every integral after that, though, is just going to be the same. You're going to be integrating circles. So remember last unit, maybe you were given a semicircle, maybe you're given a right triangle, maybe you're given a square. These will all be circular. Okay, so let's just dive right in and we'll start looking at some examples. And just as a quick disclaimer, I'm not going in order of your notes in terms of just A, B, C, D, E. I'm going to jump around a bit. So I just kind of watch what example I'm on. But we will start with A. So I have this region, and it's I think it's our exact same region that we had last unit. It's a nice region when we start squaring because it's the square root there. So I'm going to take a look at x equals 6, which is a vertical line, y equals 0, which is a horizontal line, and the square root of x minus 2. And I'm going to revolve that around y equals -1, which is a horizontal line. Now, I kind of did the first one for you. I zoomed in, and what I want us to think about here, maybe I'll take this one, right, is that whatever this region is, like whatever that original region is, right, and I revolve it around this line, y equals -1, I have to always still preserve distance and preserve symmetry. So if I know that there's a gap of 1 that's in between the curve and the line of rotation, then the lower boundary also has a gap of 1. So if I were constructing that up here, I would say, okay, here's my line of symmetry, line of rotation, and then I would just draw its mirror image. Like that's the I think the most helpful thing to do is draw that mirror image. Here's what it looks like when reflected over the line, y equals -1. And then what I would do is I'd go up to the original and I'd say, okay, here's what's going to be one of our central radiuses. Like that's going to be the thickness. That's going to be the thickness of one of our disks here. And then I just replicate that down below. And try to make a circular hole and a circular boundary. And we start doing these; they start looking like eyeballs, I think, or olives. But the idea here is that you're trying to somehow create a circular disc or circular washer that represents the one of these particular shapes. And again, remember this thing's going around and rotating around, and so like you could get. It reminds me again maybe like some artwork like pottery, or bowls, or this looks somewhat like a melon or something like that. So, but once you understand, I guess, what's happening with that rotation, that's all you really need. And you don't have to go crazy drawing a three-dimensional shape. What I want to next identify is what's the larger radius. So this out here represents the edge of the exterior of that disk. So that right there is going to represent the largest radius. And if I want to, okay, then I measure, okay, this right here, that distance there represents the inner radius, the radius that I'm taking away. And again, go back up and compare what we did, just two-dimensionally. We had an outer radius, a big circle that we found its area, and then we subtracted a smaller circle. So that's what we're doing. That's the formula that we're going to integrate. I want to identify the larger radius and then the smaller radius. Now the larger radius, notice the larger radius is going to be bound by this top function, and then the smaller radius is going to be bound by this lower function. Okay, so let's kind of start putting this together. And again, you might want to watch it and just see it the first time and then replay it and set it up again. Okay, so I'm going to be integrating. Now these disks start here at 2 and end over here at 6. So those are my boundaries. So 2, 3, 4, 5, 6, 7. Oh, actually 7, I'm sorry. Did I say 6 up here? I feel like I did. X equals 6. So 1, 2, 3, 4, 5, 6. So my diagram's off. Like this one, 2, 3, 4, 5, 6. This one's correct. This one I have just a little bit too big. So we're going to stop it at 6, like the direction said. 1, 2, 3, 4, 5, 6, right there, right? 1, 2, 3, 4, 5, 6, which would have been here. So I don't need that extra one. So we'll go from 2 to 6. Sorry about that. So we're going to go 2 to 6. And I'm always going to factor out my pi. And I'm looking for big R squared minus little r squared. We're perpendicular to the x-axis, at least in terms of that rotation. So it's going to be in terms of x. So let's identify this big radius. This big radius has an upper boundary of this function. and has a lower boundary of this blue line. And again, thinking about measuring that distance, from up here to here, like that distance right there is this radius. So the upper boundary is the function, and the lower boundary happens to be this y equals -1. So if I measure that distance, it's just top minus bottom. So it would be the square root of x minus 2 minus -1 squared. This right here, it would be the top all the way down to the bottom. The top to the bottom. And notice this minus and negative, that's going to clean up and become a plus sign. I get it. I like seeing that minus and negative because we're going to find when you do top minus bottom, it's subtraction. And if you are lower than the x-axis, then it becomes a minus and negatives. But I like that. Okay, minus, and then we go to the smaller one. Now, the smaller one, this radius has a boundary that's on the line y equals 0, and it has a lower boundary of y equals -1. So then I'd say that's 0 minus -1 squared dx. And then don't forget, let's put our integral symbol on from 2 to 6, and then there's pi. Okay, a couple things I want you to focus on, and maybe obvious, maybe not obvious. Okay, first, notice that the position of our two functions, those were the boundaries of our original region. The top was the root x minus 2. The bottom was 0. And they're always going to be in the same relative spot. They're either both first or they're both second. In most cases, it'll be both first. Okay, second. Look at what this, you're doing the same operation with that line of rotation. You're subtracting that line of rotation. Again, it's symmetric. It has the same setup. They're both squared. And then one of the most common things that you see on the AP exam is forget pi, because remember, these are circles. It's pi r squared minus pi r squared. Okay. And honestly, I leave my answers like this sometimes because it shows me the structure that it does, in fact, do the function minus the line of rotation squared to measure the first radius, and then the function minus that's the big R squared, and then the function minus the line of rotation squared. So big R squared minus little r squared. Okay, so we're going to do a couple of examples. Again, just setting that up. Once we get it, I don't care about the integral at this point. I just want the setup. And you can leave it as unsimplified and as raw as this, but I also think that that tells you a lot about what's happening within this particular revolution. Okay, so now it's the exact same region. Notice I'm going to go to example D next. I said I was going to go out of order. So I want to rotate this around y equals -2. I'm going to actually draw in y equals -2 is my line of rotation. So there's y equals -2. And if you remember, it was like whatever this distance is, we're going to mimic it and mirror it down below. So try to draw what would that reflected image look like. So here it is up here it is down below. Okay, and then go ahead and draw one typical radius, like measuring from top to bottom. So going from here to here, like that distance there should be exactly the same distance there. And that sort of gives you kind of like nice little anchor points. So then you can make that circle go around so that the line is like basically that center. So here would be the inner circle. And again, trying to make it perspective drawing. So you're almost making it like an oval or an eye, like an eyelid. And then try to keep a uniform thickness going around. And I feel like I do better on pencil and paper than on this tablet, so I apologize. But you do get better over time. So this circular region right here, that represents my disk. I'm going to have a lot of these disks that I'm stacking up. And as long as I know what one looks like visually, like so here's this disk, emphasize that. right? Even though, I know I'm going to get lots of them, they're going to stack. Like there's going to be one that's going to be down here that's going to be the bottom, right? Circular, and there's going to be one over here that's going to represent the top, and then it'll be cut out. But I really just need that one. I just need one to say, okay, what's my big radius? What's my little radius? And if you want to like draw it out off to the side, your larger radius will be from the farthest function away from the line of rotation. And then your smaller radius would be the one that's closest to your line of rotation. And I realize that the only thing that's changed in this example is our line of rotation, but even just going through and setting this up, I think is so important. So we are looking at pi r squared minus r squared as an integral is perpendicular to the x-axis from 2 to 6. And that just kind of gives me my structure. And remember, the radius, to find this radius, it's going to involve the function minus the line of rotation. So that would be kind of like my next step. Okay, so pi from 2 to 6. Okay, so then again, same upper function, which is the square root of x minus 2, and then minus negative 2 squared. So this again represents our big R. That's our, our top distance down to the bottom distance. So that represents the outside circle, right? That's the radius of that outside circle. So then if I just did this, it would be completely filled in, right? I'd be completely filled in. There'd be no hole whatsoever. I just have the area of one circle. But then I'm going to take away the center part. So I want to take away, that part. So eraser didn't really do what I wanted to do. So then to do that, I'm going to say, okay, minus, go back to like maybe this color and go to thin. So minus the radius, so starts at 0 again, minus negative 2 squared dx. And again, that would represent this lower function going down to the line of radius and then taking away this right there. So if I remove that, I would get my original disk. Okay. And again, look at the symmetry. I don't want to under stress this. I really, really want to make this a good point. Here's the top function. Here's the bottom function. They're positioned in the exact same location and structure of this particular integral. Here's your line of rotation. Here's your line of rotation. Here's your line of rotation. Don't forget the pi, right? It's like dessert. Don't forget the pi. Okay, let's see. Let's go maybe one more example on this video, just because, again, I want us to really, really get a good feel for this. Okay, now we're going to just rotate about the x-axis. So same shape. Okay, here's our line of rotation right here. Right, line of rotation. Let's see, go blue so we can see a little bit better. So there's our line of rotation. So then again, I would just draw the image over. So, just reflect it over. So there it is. And then, so I have this image here. And then if just draw in just one, maybe one line here. And wherever that is, it's going to be mimicked down here. Now, because there's no gap in the middle, this is going to be a solid figure. So when I go and rotate this to get this disk, right, it's just going to be a circle. It's just going to be a completely filled in circle. So when I'm taking away my inner radius, the inner radius is actually going to be a value of 0. But I'm still going to show that because I think the more consistent you look at these problems, the better. So here's that one circle with a radius right there. So again, thinking about, okay, here's our big radius, and our little radius is just a dot. It's just the x-axis, right? We're not taking anything away. But you could still start out this structure. pi integral from 2 to 6 of big R squared minus little r squared, and will be in terms of x. And kind of just as a little preview of the next video, what if you start rotating the other direction? You'd be starting to be in terms of y. So just as a heads up. Okay, upper function is still our friend, the same function. So from 2 to 6, it's the square root of x minus 2 minus 0, our line of rotation, squared. So this again represents our big R right there. And then I'm going to still say, okay, well, what is the radius of our small one? Well, there is no radius, so it's 0. And we're rotating that around the line 0, and then we square it. And again, unnecessary. Like you could walk in and say, wait, why is that there? Right? But remember, I like that structure, the symmetry. I like saying, here's the top function, here's the bottom function of my boundary. Here's the line of rotation, here's the line of rotation. And then I also see that I have pi. Okay, so a lot on that, right? And again, going through and going over these examples and pausing it and trying on your own, erasing it, trying on your own, I think is super, super helpful. Okay, so when we look at our next example, as you can see, and I'll do this in the next video, we're going to rotate the other direction. So let me take a break. Let me pause this, and I'll start the next video with example B, and in that case, we'll be going around the other axes. So, excellent.